Good morning, calculus nerds. What else would you be doing this morning? Today is Monday, but it's also McKenna Thursday when you think about it, right? And tomorrow's Tuesday, but it's really Friday, so we have a short week. Okay? So I don't know what they tell you in advanced algebra or FST or pre-calc, but do they ever explain the difference between what an implicit equation is and an explicit equation? Okay. Do they ever tell you the difference between equations and functions? Does anybody know the difference between an equation and a function? Yeah.
I know an equation has a set solution and a function typically doesn't.
Okay. Can I give you the definition of my definition of an equation, a function? An equation is a mathematical sentence that has an equal sign, and a function is a mathematical sentence that has an equal sign, but you're guaranteed only one y for every x. Okay? So this is one of my favorite equations that is not a function. This one right here. You know what that equation, what shape that equation makes? No one knows? I'll try to make one. In fact, we had a class at Bemidji State where we practiced making these on the chalkboard. We had to practice for like a week. Talk about a painful experience. It's this thing. You know what I'm attempting to draw?
A
Circle. You know what the radius is? 5. So this point right here is 5, 0. This point right here is 0, 5. This point right here is -5, 0. And this point is 0, -5. Okay? That's an equation, right? But it's not a function, is it? Correct? This equation is what we call in implicit form. In my brain, implicit form means x and y are working together. In other words, I squared x, I squared y, and then what did I do? I add them together. So all of these right here in your notes, these are all implicit equations. Everything in this column. Because x and y in tandem are working together. Now, sometimes, a lot of times, we can write them explicitly. What do I mean by that? Well, that means y gets defined in terms of x. So in other words, y is by itself. Okay? So Jeremiah, this one right here, can you tell me what y is by itself? Can you kind of do that in your head?
Yeah.
What would you write?
2/3 x plus 3.
You're close. You're really close.
Plus
You're still getting closer. What happens when the 2x, how do you get the 2x over to the right side? Would you agree it's a -2/3 x plus 2? Okay, you're okay with that? Do you see how we kind of change it? Everybody agree with that? This is called explicit form, correct? Y is by itself. Tyler, what about this one? Can you do that one in your head?
would be a -x plus 5.
How'd you get that?
Subtract x squared.
Okay, so I get 25, so I get y squared equals 25 minus x squared, correct? Okay, and then what am I going to do next? Okay, and if I take the square root, what do I get as an answer? Agree with that? If I take the square root of both sides, do I get 4 plus 3? Do I get this? And that is not this. Right? So what do I get? Okay. Almost something else I need. I need the plus or minus outside here, right? And that plus or minus tells me that that is not a function because I get 2 y's for every x, right? And if I look at my beautiful drawing I have here, right here, here's an x value. I don't know, make it 2. I'm going to have a y value down here. I'm going to have a y value right here. Let's see, it's, what'd you say, y equals plus or minus the square root of 25 minus x squared. So I'd get 2 comma square root of 21, 2 comma negative square root of 21, right? You okay with that? Okay. You want to try this one in your head? Okay. And Hannah, you want to try this one, right? Which is a parabola, right? So this one would be a function, wouldn't it? Right? And what about this one?
Y equals 1 over x.
All right. I'm going to shift a little bit, and I'm going to show you something that I got on my calculator, my phone. I call it my calculator. And it is a app called Desmos. I don't know, does anybody else have that? I know I've had you do activities on Desmos, but you can get it as an app. I love it. I'm going to show you one. Oh, shoot it. It disappeared when I closed it out. All right, I'm going to. If you turn to the back side, there's crazy function number 5, and I'm going to get to it in a second. Do you see where it says y to the 4th? Okay, you can't do this on a Casio or a TI, but I can do it in Desmos. So I can take y to the 4th plus, hard part is using my fingers, y to the 3rd minus 3y minus 5x to the 5th equals. So it allows me to enter an equation implicitly. And it looks like that. That's obviously not a function, but at least you got this implicit equation and see what it looks like. Isn't that cool? Okay. And so that's what Desmos allows. I do that a lot, Gullen, because I need to know what these crazy functions kind of look like, and that's what allows me to do. So it's a free app that allows you to do that. So let's get back to this. And what we're going to do is, well, that function number 5, would you agree that would be really, really, really difficult to get y by itself? Incredibly difficult. But if you look at this graph, it has points on it, correct? And so you can create tangent lines there, right? And those tangent lines have slope. So we're able to determine slopes of tangent lines on equations that are not functions. What allows us to do that is we take the derivative of an equation that's in implicit form. What do I mean by that? That y and x work together. They're in this form right here. So it's a technique we're going to use. Now you don't always have to use it. You could always write it in this form and then take the derivative just like you normally do. Like the derivative of this would be 2x. Would everybody agree? Okay. So we're going to talk about, first of all, differentiating with respect to x. And I'm going to start out with some really, really easy ones and tell you what I mean by that. First of all, I'm going to start out with a simple one. And I'm going to have y equals x. When I take the derivative, I really can write this. dy dx is equal to dx over dx. What I am saying when I say that is the change in y over the change in x is equal to the change in x over the change in x. Now, what do you suppose dx over dx is? 1. Yes, ma'am.
Is that equation true
Of all derivatives. Okay, so let's look at this one. Are you asking like something like this? Okay, so what that means is I can write it like this. Would you agree? Okay, this is what I call in composite form. Okay, and so I'm going to use the chain rule, so I'm kind of jumping ahead a little bit. Okay, so I could bring down, there's a 1 right here, correct? There's a 1 right here, correct? 1 times 1 is 1. Then I'd get y to the 0 power. And then when I take the derivative of y, I get dy dx. Over here I'd get 2 times 1, which is 2. Then I'd have the 0 power, and then I'd take the derivative of x with respect to x. Derivative of x with respect to x. And I would have something like this, dx over dx. Now, 1 is 1, obviously, right? What's y the 0 power? 1. So here I have 1 times dy dx. And over here I have 2 times 1 times, this also is 1. So you can see that, oops, I made a mistake here. You guys can yell at me. This should have been a 1, right? Using the power rule, correct? Would everybody agree? So this should be an x, not a 1. Sorry about that. So you can see that dy dx is equal to 2x. Is that making sense? Now, this is differentiating with respect to x, where x, right, the slope of the tangent line is dependent upon x. Does that kind of make sense? Okay. Over here, what if I did it with respect to a different variable, respect to time? So, in other words, imagine that I have a function And on that function, I have a point. And it's moving along this point. Well, when it gets up to here, dy or y is not moving up very fast. Would you agree? So not only does y have a speed, x has a speed as it moves along that curve. Does that make sense? So what I can do in calculus is if I have something like this, and let me draw another graph. And this is the equation y equals x squared. If I start here and I go down, would you agree that y is going down faster than x is y is going down faster than x is going to the right? Would you agree with that? So if I take the derivative with respect to time, and we're not going to do that today, we could say, okay, this is y to the first power, this is x to the second power, and if I take the derivative with respect to time, I'd have a 1 here, I'd have a y to the 0 power, and then I'd have the change in y over the change in time. That's how fast y is moving. Equals 2x to the first times dx dt. That's how fast x is moving. Does that make sense? Okay, that's where we're headed towards, because we're going to have things changing with respect to time. We change with respect to time. My volume has changed with respect to time. The amount of hair on my head has changed with respect to time. Correct? So we're looking at implicit differentiation, and later on we're going to talk about it, how these variables change with respect to time. Is that kind of making sense? So if I have this one, and the example I'm going to bring up is this one right here, x squared plus y squared equals 25. I can write this as, I'm going to take the derivative. I'm not going to get y by itself. When I take the derivative, where x and y are working together to find a value, where one is not separate from the other, that is called implicit differentiation. And so when I take the derivative of this, I'm going to take the derivative of this. I could write dx dx. I took the derivative of this variable with respect to x. I took the derivative of this, and remember, I'm kind of using the chain rule right here. And I'll put that in here. And when I take the derivative of y, I'm going to write dy dx. And anytime I take the derivative of any constant, I always get what as my answer? 0. So this is going to be a 2. This is going to be an x. This is going to be a 1. This is going to be a 2. This is going to be a y. This is going to be dy dx. This is 0. So dy dx is equal to a negative 2x over 2y. which is equal to a negative x over y. Everybody with me so far? Any algebra that I did that's confusing or anything that I need to explain? This gives me, this is an equation that gives me the slope of the tangent line, which means my inputs are just not x anymore. My input is also y. Does that make sense? So I'm going to draw this graph, and I'm going to do it right over here. I'm going to back up a little bit. And here's my graph. And I'm going to pick this point right here. That point is 0, 5. And dy dx is equal to a negative x over y. So I get 0 over 5. Did everybody see where I get 0 over 5 when I put that in? So what's the slope of this tangent line here? 0. It should be 0. It's a horizontal line, isn't it? Does that make sense? Now, let's look at this one. There's my tangent line. It's what kind of tangent line? Vertical. Its slope should be undefined, correct? Its slope should be undefined. So this point is a negative 5, 0. So dy dx is equal to a negative x over y. Don't I get 5 over 0 at that point? Isn't that an undefined slope? Isn't that the slope of a vertical line? This point right here. This point right here is, that's 1. So that's going to be 1, negative square root of 24. That's what the point is. Does everybody know where I got that? Right? The square root of 25 minus x squared, right? Plus or minus. So that means dy dx is equal to a negative x over y. I'm going to have a negative 1 over a negative 24, square root of 24. Well, that's a positive 1 over the square root of 24. That slope should be positive right there, shouldn't it? Are we okay? Now, I give you some guidelines for when you do implicit differentiation. You want to differentiate both sides of the equation with respect to x. What does that mean? Dx will be on the bottom. Collect all terms involving dy dx on one side of the equation and remove all the other terms to the opposite side. If you need to, factor out dy dx from the collected terms, solve for dy dx. Now, this one, I know you can get y by itself and figure it out, correct? In fact, if we did that, we would do this, and I think this is what Jeremiah gave us, a negative 2/3 x plus 2, correct? Right, Jeremiah? I don't want you to give that up. This one's an easy one to do. I should get dy dx is equal to a negative 2/3. Would you agree with that? But if I do implicit differentiation, I should get that same answer. I'm going to get 2. Do you want me to write dx over dx? Are we okay where that it's going to be 1 anyway? We're okay with that? So then I'm going to get plus 3 times dy dx. Every time I take the derivative of y, I'm going to multiply by dy dx. Every time. Remember, this is 3y to the first. When I take the derivative, I'm going to get 3y to the 0 times dy dx. That's where this comes from. Equals, what's the derivative of 6? 0, because the derivative of any constant is always 0. So that means dy dx, I'm going to subtract the 2, it'll be negative, and then I'm going to divide by 3, gives me a negative 2/3. Now again, I could very easily, and I would encourage you still to do this, is get y by itself when it's easy like this, and take the derivative, just like you have been doing, and get 2x, right? That's how we would do it explicitly. Implicitly, it'd look like this. Dy dx minus 2x times dx over dx, right? I'm not going to write that anymore, and we're okay with that? Does everybody agree? Equals 0. Then I would add 2x to both sides, and I get dy dx is equal to 2x. Now, these are easy ones, right? They're very friendly, because you could have done them like this, like you've done in the past. Turn it over. Here's this one. I think we already did it on where it says b using the chain rule, correct? Okay, I'll do it again. 2x plus 2y dy dx equals 0. dy dx. If I subtract, I'll get a negative 2x divided by 2y, which is a negative x over y. Again, this is the formula that gives me the slope of the tangent line. Now, this one, I could do it explicitly. I could write y equals 1 over x. Would you agree? Correct? Equals x to the negative 1 power. Would you agree? So dy dx would equal a negative x to the negative 2 power. Would you agree? And that would give me a negative 1 over x squared. Would you agree with that? Or I can do it implicitly. Now, Hillary, will you tell me how y and x are working in cooperation to get 1? What are they doing exactly? Right. You would say x times y equals 1, correct? Well, because as soon as I have you say the words times or multiplying, what are you thinking about up the product rule? So I'm going to take x times the derivative of y, which is dy dx, plus y times the derivative of x, which I could write as dx over dx, or what? 1 is equal to 0. Now that means dy dx is equal to a negative y over x. Does everybody see the algebra I did there? how are these the same? One's in terms of x, and the other one says, okay, you can get the same answer if you use y and x. How can I get this one to look like this? How's that even possible? Do I have a name for y in terms of x? Hillary, do I? Do I know what y is? So I could say this. I could bring this baby down and say what this is a negative 1 over x, which is a negative 1 over x times the reciprocal of x, which is 1 over x, which is this. All I'm showing you, you don't have to get this to look like this. I'm just saying they're equivalent. A different name for the same thing. Look at this. This is where implicit differentiation is really, really good. Because you cannot, well, you can. You can get y by itself, but it'll probably take a couple of days to do. You have to know how to, do you remember ever learning about completing the square?
Yeah.
Well, you can complete a cube and you complete a quartic. A quartic is something to the 4th power. It takes you an unbelievable long time. I've done it. Took me, I worked on this problem for 3 years, and I finally could figure it out once I found out that you can complete a quartic. So I'd have to complete a quartic here and a cubic. Sawyer, it's a painful experience. Okay? So you don't want to do that. What you want to do is do implicit differentiation. So let's give it a go. Gabby, y to the 4th. Implicitly, what would the derivative be? Do you have an idea? Okay, 4y to the 3rd. Then I got to multiply it by what? Remember, you got to kind of think of it like this. There's 4, that's why there's a 3rd, and then inside I got to take that derivative, which is, no, it's not 1. If it was dx over dx, it would be 1, but it's dy over dx. Okay. Again, McKenna, this is like y to the 3rd, right? So I'm going to write plus what? Times. Yeah, every single time you see that y. Gavin, I'll put the minus sign there for you.
3 times dy over dx.
Yeah, and I got 3 dy over dx's, don't I? We'll talk about how to deal with them. Elizabeth, what's the derivative of that? I'll put the minus sign there for you. How about 25x to the 4th? Okay. Yeah, dx over dx. I'm not going to write dx over dx because it is the equivalent to what? 1. Everybody okay on that? Equals. What, Sawyer? What's the derivative of 17? 0. Okay? Now, if you notice, I have 1, 2, 3 dy dx's. I have one term that doesn't have dy dx, does it? So I'm going to move this over here and get 25x to the 4th. So now I'm just left with these. So there's a dy dx in each of these, isn't there? Correct? So I'm going to factor out the dy dx. Does that make sense that I can do that? So I'm going to factor this out. Really what I'm doing is I'm reversing the distributive property, right? And I get y cubed plus 3y squared minus 3. And then I'm going to divide both sides by that quantity. So dy dx is equal to 25x to the fourth over 4y cubed plus 3y squared minus 3. What does this give you? If I know the point that's on this graph, if I know a point that's on this graph, I plug in x in here, y down here, and I'll know the slope of the tangent line at that point. All right. We're going to skip number 6. We'll come back to it, and we'll finish up with it tomorrow. Does that sound good? We're going to go to number 7. Read, here's the key word, equation of a line. It doesn't even have to be tangent, of any line. What two things do I need? Slope. And guess what right here? We got the point. Right? So we're halfway done. We just got to figure out the slope. So here I am, x cubed plus 4y squared equals 3. Read, what's the derivative of x cubed?
3x.
Right, and you could say dx over dx. Well, it's kind of like a pointless thing to do, right? Plus, here's the hard one. What's the derivative of this? Times dy over dx equals what? 0. So in your head, move it. What's my formula that gives me my tangent line? Perfect. Okay? So now I'm going to figure out the slope of my tangent line. What am I plugging in for x? And you're going to square it. And then you're going to multiply by a negative 3. What are you going to get? Beautiful. Then you're going to come down here and you're going to plug in what? 4. Because that's your y value, isn't it? And you're going to get what? 8. There's the slope of your tangent line. So my equation is a negative 3/8 parentheses x minus a negative 1 plus 1, or negative 3/8 x plus 1 plus 1. Is that making sense, Reed? Because we could get y by itself in here, but do you see why you would have two equations or two functions to take the derivative of? Because you're going to get plus or minus in front of that square root, right? All right. See you guys tomorrow. Face up.